but it's always a rate of change. Something is changing as a function of something else. Where did the marker go? So the first concept that we want to appreciate is there's a difference between average rate of change. I don't need these ones anymore. Okay. So there's instantaneous versus, I have to get some other markers, versus E. Versus average. Average rate of change. So they're both a rate of change, right? They're both measured in meters per second. But one of them, if I now draw, so we say, well, it's not true that I went in a straight line. My speed was not constant everywhere. My speed changed. I went a little bit, and then faster, and then I slowed down, then I went very fast, and then where's my 9 seconds? And I didn't, there. Yeah? This is more what I did. I don't want that, I don't want this. So now, if you move like Linda, then you move at a fixed speed the whole time, and the slope will be the same throughout. It's a constant slope. Then it's easy to calculate the slope. You can pick any 2 points, doesn't matter where, any 2 points on the line. Yeah, you could take here and here, you could take here and there, and you measure what is the difference in the height divided by the difference horizontally, or this height divided by this distance, and you will always find the same answer. That's why we say this is the slope of the line. It's the same slope everywhere on the line. So you can choose any 2 points on the line and calculate the slope, you get the same answer. But with this curve, and this is now, so this is her speed. And in this case, when you have a straight line, the average speed, which is the total distance divided by the total time, this will give you a speed, which will be a slope, right? And it will be the same as if I measured the speed at any point on the line, from here to there, from here to here, from here to there. So her instantaneous speed is the same everywhere. Where am I? Room 6. Yep. Thank you. But in some other cases, and in life in general, things don't usually move in a straight line. They go faster and slower. And so, but we still have the same question, is how fast was I going at this moment? At this moment, how fast was I going? Maybe compared to this moment, or compared to this moment, how fast was I going? Now, how do we answer that question? Yeah?
You say to find the total average, we can divide it both from the points, origin point to the is divided by time. And you say we can make any point like where give us same answer.
Yeah. You want to test it? Should we test it? Should we try it?
Yeah.
Okay. I'm going to use some, let's just say 7 meters and, well, this will be fun, and 9 seconds. Okay, so we'll say this point is the point 7, 9. Okay? And here is the point 0, 0. Wait, that's going to be messy. Okay, that's fine. Is it fine? No, it's going to get messy. I'm going to cheat a bit. Okay. Not cheat. I'm going to pick a different line just to make our life easier. 5 and 10. This is 10, 5. Oh, nobody corrected me before. I wrote it backwards. It wasn't 7, 9, it was 9, 7. But now we're going to use 10 and 5. So 5 meters, 10 seconds, 5 meters. Okay, what is the average speed over the whole distance? Five divided by 10. Okay, so the average speed is 0.5 meters per second. Let's choose 2, 1. We have different points. We can choose anything. Let's go 8. This is 8 and 4. We have 6 and 3. And we have 4 and 2. Which points do you want to? We can use other points too. These are the easiest. We can also have, if you want, 3, 1.5. And we have 7, 3.5. So, Linda, you calculate the speed from this point to this point. Okay? From 2, 1 to 4, 2. You go 3, 1.5 to 7, 3.5. Ishmael, do 2, 1 to 8, 4. Yeah? Loveness, 6, 3 to 7, 3.5. Charles, from 4, 2 to 10, 5. And Mike, from 3, 1.5 to 4, 2. So you should all know how to calculate a slope by now. All right? Delta y divided by delta x. So I gave each of you 2 points. So you take the y values of the 2 points. I shouldn't need to explain. You should know this already. Yours are from here to here. 3, 1.5 to 4, 2.
So, y means distance.
Mm-hmm. So everyone has different points. So we're going to see what speed everybody calculates. And Timothy, Ishmael, Ashton, Mike, and Kyle. As soon as you have your answer, you can tell me. You have yours? Loveness has 0.5. Okay. Who? Charles? Okay. Okay, same answer. Linda, what did you get? Mike gets 0.5. If someone needs help, go ask a classmate who's done. Ask someone who's finished already. Loveness or Mike or Charles. Which numbers, which points are you using?
7.
7, comma, what is this number? Uh-huh. And you found how much?
2.
2 what? You measured 2?
Yeah. 2 to 7.
This one? That was yours? Who? Ishmael. You're saying you calculated 2. Is your answer? From this point to what, to this point? These are these your points?
Yeah.
Okay. Is that yours or his? Yours. 0.5. You also get 0.5. Okay. We're left. Timothy's not here. So everybody got 0.5 except Ishmael. So we'll come back and see how Ishmael got 2. What was our average speed?
0.5.
Okay. And what did everybody calculate? Are you surprised? Ishmael, how did you calculate 2? Let's go through the steps. Do you know what was your mistake? Yeah? You were calculating, you should calculate slow.
Then it's okay. Then it's okay too.
So tell us how you did the steps. So you had 4, comma 2, 4, 2, and 7, 3.5? Okay, so how did you do the calculation?
Okay. I did y. So
Okay.
4 is x1.
So this is x1, y1. This is x2, comma y2. So what next?
Then I took x2 minus.
Which is 7? Minus.
No, I mean y2 minus y1.
Okay, so 3.5 minus 2.
Divided by 7 minus 4.
7 minus 4? Okay. So what is this? 3.5 minus 2? That's 1.5 divided by 7 minus 4? 3. So what is 1.5 divided by 3? 0.5. So where did we get 2?
I made a mistake. I took 3 and it was only.
You did 3 divided by 1.5 instead of 1.5 divided by. because the inverse of 0.5 is 2. So everybody gets the same answer, 0.5. That's what it means to be the slope of a line, is that everywhere on the line, from any point on the line to any other point, the rate at which it increases or decreases is the same everywhere. Yeah? That's what this number is saying. It's saying for every second, so if I go from 1 second to another second, I will go up by 0.5 meters.
You solve my point.
Okay, I thought you did it. You want to do it? Okay, what are your numbers? 3,15 and
7,115.
okay. So what do we do?
Changing distance. D is the element numbers. I think quite also. D is distance. 1.5 is time.
This is 1, 2, 3 seconds, and oh, yeah, that's right. It's not aligned very nicely. This is supposed to go here. That's why my scale isn't very good. But this is correct for the line. You're okay? My drawing is not exactly to scale, so if you're trying to read here, yeah, it looks a bit off. But I promise you that these numbers are correct. You can check it later if you want. So a line has a constant slope, and the slope is basically this number tells you every time you go 1 horizontal unit, how much do you go up? Here you go up by 0.5 meters per second. So for every 1 second, I go up half a meter. Another second, another half a meter. Another second, another half meter. Another second, another half meter. And so if I take 5 seconds, then I go up 5 half meters. So I would have 2.5 meters divided by 5 seconds, 0.5 meters per second. Yeah? So the slope of a line is everywhere the same. So the instantaneous rate of change for a straight line is the same as the average everywhere. This is simple. So if you ask how fast is Linda going at this moment, 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 you will get the same answer because she's walking at a fixed speed. But in life, most things don't move at a fixed speed. They go faster, slower. And so, but we are still interested in the question often, how fast is it changing in this moment? And so what we will do then, how do we find that out? Is, and again, I think we've introduced this before. So now I might have something that moves like this. It starts, it reaches 3 meters very quickly, and then it doesn't move very far, and then it moves again, and then it slows down. So this one is going, yeah, if you think about, after 1 second, where is it? It's about 1.5 meters. After 2 seconds, where is it? 3.5 meters. After 3 seconds, still 3.5 meters. 4 seconds, 2.6 meters. 5, 6, not very much. 7, it's not even at 3 meters yet. So look, from 3 seconds to 7 seconds, it really didn't move very much. It went from here to here, almost not moving, right? So this was very slow. And the slope here, if you were to think of this as a straight line, the slope would be very close to 0. It's almost a flat line, right? From this point now at 8 seconds, now we're at 4 meters. Now we're moving again. At 9 seconds, we're at 5.5 meters. Ooh, in 1 second, we went from 4 to 5.5. That's a lot faster than we were doing here. And then at 10 seconds, we're at 6 meters. And then you could break it down to even smaller pieces to see that. So the point is, this is describing someone who is moving, but not at a constant speed. And then this would be the opposite of what I did. Started fast, went slow in the middle, and then went fast at the end. Right? So how would we, now you ask, what is the speed of this person at this moment? Exactly at that moment. Well, it's not a straight line. How do you calculate a speed, a slope, when it's not a straight line? And the answer is you draw a tangent line. Do you remember tangent lines? So a tangent line is a straight line, and a straight line has a slope. And this straight line touches the curve. So now we have a curve function. The tangent will touch the curve only at that point. It doesn't touch anywhere else. Yeah? I did this in class a while back, I remember. And I said, for example, if I go, my head is curved, and I can just touch at one point. Here it's like this, here it's like this, here it's like this. Yeah? So you can make a tangent at different points on the curve. Then, now that I have a straight line, well, then it has a slope. And I will define that the slope of this tangent, so the slope of the tangent is the instantaneous rate of change. The slope of the tangent line is the instantaneous rate of change. Huh? So at this point, we could say my line is going up very fast, right? So this would have a high rate of change. And then as I go along here, to be a tangent, I have to go like this. Now it's a very low rate of change. As I reach here, I have to go up like this, and then like that, and then like this again. And you see that as the angle of the tangent line changes, then there's a change in the instantaneous. There's a difference in the instantaneous rate of change, and that is given by the slope of the tangent line. The reason that we studied limits before is now, so we have defined, we say, okay, fine. We will define that let me draw a proper one, that the slope of the tangent line is the instantaneous rate of change at the point where it is tangent. So a tangent line is tangent at one point. Every point on the curve has its own tangent line. Yeah? So if I go a little bit here, this one has its own tangent line, like this. If I go here, this one has this tangent line. If I go here, it has this tangent line. Every point has its own tangent line. Every tangent line has its own slope, right? These are, clearly they have different slopes, right? And therefore, at every point, there's a different instantaneous rate of change.
So, what can we, how can we find the average speed using that tangent line?
If you want the average speed, you don't need a tangent line. Average speed is defined from one point to another point on the curve. So if you want so average speed Average rate of change between 2 points on the curve. An average is always between 2 points on the curve. There's no such thing as the average at a point. Then it's instantaneous. It's at that instant. That's the instantaneous at one point. If it's from this point to that point, then it's now an average. Okay? You can imagine when you are on a kabaza, starting from home to come to campus. Yeah? And I asked, how fast are you going on average to reach here? You say, that's easy. I calculate the total distance from home to here. I divide by the amount of time. That's my average speed. Now, if I say, does that mean the kabaza was going the same speed the entire way? No, he had to stop. Here he went down the hill, it was going faster, and then he was going up the hill, there was traffic, he went, yeah, the speed was changing the whole time. But I asked from the beginning to the end, what was the average speed? You don't care about the in-between, you just say, from here to there, the distance is what? And the total time is what? That's the average speed. Now, we will use average speed to calculate. So right now we've said, okay, this is how I define the instantaneous rate of change as the slope of the tangent. But now, how do I calculate that slope? I don't know, do I have enough information? And this is where we will now define the derivative. And the derivative, and this is where we use the concept of limits. I'm doing on time. Okay. So, don't need this anymore. I wish I had a better marker, but anyway. Do you think there's a better marker next door? I didn't, let me just go check quickly. Does somebody want to go see if they can find a better? Let me just check next door quick. Hello. I'm looking for markers. There are lots of markers. I don't know if any of them are good. Probably not. Lots of markers. Let's hope one of them is okay. Probably not. No. Okay. Does somebody want to volunteer to go find a better marker? Volunteer, not voluntel. And you can throw these out, or ask them to throw it out. Thanks, Justin. Okay, so how do we calculate a derivative? All we have is the function. And when we say we have the function, that means I know the coordinates of every point on the line, right? That's what it means to know the function. The function is, if I give you a number on the horizontal axis, you can give me the number on the y-axis, on the vertical axis, and so I know the coordinates. Okay, but I don't know any points here on the line. So how do I calculate the slope of that line? Because to calculate a slope, we need 2 points, right? With us? Okay, so we need 2 points. So here's where we take a secant. Anybody remember what is the secant? Loveness. Hey, secant, S-E-C-A-N-T, is a line segment that joins 2 points on a curve. So if I chose this point and I draw a line, this is the secant line from point, call it P, to point Q. This is the secant PQ. Yep. It's just a straight line between 2 points on the curve. Easy? Yeah. So now we have this idea of a secant. I'm not actually interested in P and Q. That was just an example. But let me take, I'm going to use a different point for our example here. Let me take this point here and say it has a tangent and I want the slope of this tangent. So let me take a secant from here to there. Is this a better marker? Thank you, Justin. You have the gratitude of the class. So at this point, okay. So we have a secant line from here to here. I know this point in principle. We'll call that point Q. This is our point P. And we have a secant line going through P. So I can calculate the slope of PQ, right? And I will get a number, and clearly this is a different slope than the tangent line. So you might ask, why is this useful? That doesn't look anything like, I need this and you're giving me that. Okay, so I said, okay, I'll make it better. I will take a point here. Instead of Q, I'll take this point. And I will draw this new secant. And I will calculate the slope of this. I will take the y value here minus the y value here, divided by delta x of these 2 points. And you will say, okay, it's closer to this, but it's still not the same. I say, you're right. Let's do better. Let's take a point even closer, on the curve, but closer. I draw a new secant. Now it's hard to draw, right? But I keep coming closer and closer, and I draw a secant, and I calculate the slope of that secant. Now, if I keep getting closer and closer and closer and closer, so here I'm at this point, this is the point X that I'm interested. I want the slope of the tangent at the point X. Yeah? But I'm finding secants that go to a point somewhere here. I was using this, x plus 2, x plus 1, x plus a half, x plus a quarter. I'm bringing this point closer and closer to x, right? Are you paying attention? As long as you don't disturb the rest of the class. So I'm coming closer and closer to x, and I find the other point, I draw a secant, and the slope of that secant will become closer and closer to the slope of the tangent line. And in the limit, so I hope you have understood the limits, yeah? In the limit of this delta x, so I want at x, but I have a little delta x there. In the limit of that delta x approaching 0, as it gets tinier and tinier, that secant becomes smaller than the eye can see, but it's still there, right? The function is defined everywhere. Even for infinitesimally small distances, the function has different values. And I can draw a tiny little secant, or I can imagine a tiny little secant, and I can measure the slope. And those slopes will approach the slope of the tangent. And so we will define the slope of the tangent line at x as such. It will be the limit as delta x approaches 0. So here delta x was this distance. So here I have a point. This is the point x. Let me make them more different. This is the point x. And from x to this other point is delta x. And I'm making this smaller and smaller. As delta x goes to 0, this other point is coming closer and closer to the point P, right? So as delta x approaches 0, what am I taking the limit of? The slope of the secant, m secant. Now, what is m secant? We can write that down. Yep. The slope of the secant is f. We have a function. This is a function f of x, right? So we have the point P is the same as the point f of x. It's the point x, f of x, right? And the other point Q, which is coming closer to P, this has the coordinates what? X plus delta x, and f of x, x plus delta x. These are the coordinates of the 2 points. This one is x, and then the function value at x, that's the y value. Here it's x plus delta x. That's where I am on the horizontal axis. Then where am I on the vertical axis? I take this and I put it inside my function. And then that tells me what is my y value. At this point, this is where I am on the vertical axis, right? So now I have my 2 points. I can calculate my slope. So I would write, I'm going to need more space. Put it somewhere else. We'll just call it secant like this. So I need the y value of this minus the y value of this, right? If I have 2 points and I want to measure the slope of this line, I take this y value minus this y value. Yeah? Okay. Am I going too fast, too slow? Okay. F of x plus delta x, that's this one, minus this one, which is f of x. And I divide by what?
By f of x, x plus delta
X plus delta x minus x. Can we simplify this? No? Try. How?
Okay. Yeah. This delta x will be cancelled.
Delta x can't be cancelled. The which?
Maybe common factor.
So I don't need these brackets because nothing is multiplying. I have x plus delta x minus x.
Yeah.
So x minus x.
Right. That x is negative x, and that is positive. So how
Yeah.
do we maintain?
X minus x. I have a number, I subtract that number. I get 0. Right? So x minus x is 0, so I can cancel them. So then I can write f of x plus delta x minus f of x divided by delta x. This is the slope of the secant. Yeah? So it's the y value here minus the y value here divided by the delta x, which is exactly right? So it makes sense. Now we put it inside our limit. So we said that's the slope of the secant. What we want is the slope of the tangent. So the tangent will be that slope, which is f of x plus delta x minus f of x, all divided by delta x, in the limit where delta x approaches 0. And this, if I'm remembering correctly, this is the fundamental theorem of calculus. This is the derivative. This is the definition of the derivative. This is the derivative, which is another word for the instantaneous rate of change. But this is a long thing. You don't want to say this all the time. So instead, we simply say the derivative. And we write the derivative. There's a few ways you can write it. They're all correct. Some of them are more used in math. Some are more used in physics. And so you should recognize them, that they're the same. We will mostly use two of them, but I'll show you three that exist. One is to write, df over dx. And the idea of the d is inspired from what we all know, delta y over delta x, which is a change. And so one of the people who created or discovered calculus, defined it, said, okay, instead of the delta, which is like a capital D sound, this is capital D in Greek. He says, okay, I will take, because I'm taking a very small delta x, I will use the lowercase d. So it's the same idea, but this is a different thing than the delta, but it's inspired from there. So you can write df by dx. If f is a function of x, then d by dx. Another way to write it is f prime. You put an apostrophe, and we say f prime. And f prime means this. This is not the function, this is the derivative of the function, f.
What about df?
This is the derivative, you would read, this is the derivative of f with respect to x. Right now, you don't have to worry about with respect to. The reason that becomes important is when you start dealing with functions of more than one variable. So right now, we just have f of x, but I could have f of x and z. It has two inputs, then it gives you an output. You could have three inputs, 4, 5. You can have hundreds of variables in here. I'll get you in a second. And then you have to specify when you take a derivative, is the derivative for which of these variables? So then you say the derivative of f with respect to x, or in that example, with respect to z, or with respect to whichever variables you have. But for now, we just have the derivative of f. That's enough.
So the derivative is the law starting from dx.
Yes. Yeah.
So can we say a derivative is a combination?
Can we say a derivative is what? A combination of limits? It is a limit. It's one limit. It's this limit. The limit has it's the same function f, but with different inputs. This is the function f, and you put inside it, you feed in x plus delta x. And in this one, it's the same function f, but you put in x by itself. So two different numbers. You take the difference between them, and you divide by delta x. Now, you might look at this and say, I don't see how this helps me calculate anything. But it does, so we could do an example. Let me just show you the third way. I'm going to erase this now. You don't want me to erase it?
No.
Oh, okay. The third way that we write this, although usually not so much with an f, but I'll do it with an f, is a dot on top. So f dot, f prime, and df over dx are all the same thing. These are all the derivative. These are all a way of calculating the instantaneous rate of change of a function. Now, fine. I want to make one thing clear. When we write df dx, this looks like we're dividing something, right? I want you to think of this as this is not a division. This is an operation. An operation is like, this is a symbol. What symbol is this? Plus. What symbol is this? What symbol is this? Times. And this? And this? Square root. Okay? By themselves, these are not numbers, right? These are operations. This is something you use on a number, or maybe two numbers, and then something happens, right? It's an operation. D by dx, sometimes you will also see it written like this. This is the same thing. Yeah, you can put the f up here, or you can put it to the right. It's the same thing. This is one symbol. You want to think of this, it's like writing this. You can't write just this. That doesn't mean anything. This doesn't mean anything, right? It's this, 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 this. Aha, that means something, right? D by itself, for now, it doesn't mean anything. D over D, it doesn't mean anything, yeah? The thing that has meaning is d by dx. And this whole thing is the operator. Like plus is two lines. If I put just this line, you say, what is this? I don't know what to do with this. Huh? Error, exactly. So d by dx, all of these symbols together, you don't need that around it. This whole thing is an operator. This tells you, aha, with my function, I should find the slope of the tangent line of the function. That's what this operator tells me. Now, we're almost out of time. We are out of time. Do you want to keep going? Or do you want to stop? Yes. Such excitement. Okay, do you want a little short break or you're good to go? Don't need average anymore. Okay. So let's start with a very simple example that we already know the answer. Okay? Let's start with a straight line. Let's write the function of a straight line. The simplest straight line you can imagine. What is the function for the simplest, in fact, it doesn't look like this. It looks like that. Y equals x. Yeah? Very simple. Timothy, are you? Huh? Oh. You can go do it somewhere else if you want, if you don't want to follow. That's fine. If you want to use that to learn, I'm perfectly happy with it. So, this is the equation of a line. Are we agreed? Yeah? What is the slope of this line? How much? 1. What is the intercept? 0. Yeah? So let's remind ourselves, the equation of a line, generally, is y equals mx plus c. So I compare. I say there's a plus what? Nothing. So c is 0. So my intercept is 0. What is multiplying the x? 1. So the slope is 1, the intercept is 0. So my intercept is 0, and my slope is 1. Okay. So let's use this now. So we write the limit, the limit as delta x goes to 0. But now I know what my function is. What is my function?
Y is equal to X.
Yeah, y equals the function. So we also say y is f of x. So f of x is what?
Y. Oh, okay.
If this is x and y is f of x, then f of x is, as a function of x, is just x. Yeah? So my function is just, if I put in x, I get back x. I get back what I put in. Easy? Okay. So let's try that. So what am I putting in? X plus delta x. And my function just gives me the same thing back, x plus delta x. Great. Minus, what do I put here? What is f of x for my function? X. And I divide by what? Delta x. Now, can I simplify? Can I simplify? How do I simplify? So I still have the limit as delta x goes to 0. How do I simplify this?
X is
Say it louder. Say it louder.
okay. Where there X.
Justin, I know you like answering. Let's give other people a chance. Mike.
This is
The x's will cancel each other. Very good. So what are we left with? Delta x divided by delta x. Can we simplify again?
yeah.
How? So we still have the limit. That part, there's no simplifying that. Can we simplify this? Delta x divided by delta x.
1.
1. Okay, now, what is the limit of 1 as delta x approaches 0?
1.
1. Yeah? There is no delta x. This is 1. It's the number 1 everywhere. As delta x approaches 0, it's still 1. So the slope of, now, what did we say is the slope of this? We said m equals 1, right? And look, we found 1. And what did we say about straight lines? We said the slope of the line is also the instantaneous rate of change, right? So this is consistent. I have not lied to you. Yeah? So we could try it with, let's try another example. I love it. Okay. All right. So let's, y equals f of x, where f of x is what? What kind of line should we do now? Now you could choose any equation of a line. Choose some nice numbers, but the coefficients, the m and the c. So we want the equation of a line. We still want a straight line.
Y is equal to
2x plus 4. Okay. 2x plus 4. So 2x plus 4 means it will intercept at 4 and it will go up faster. 2 instead of 1. What is the slope of this? Slope is 2. Okay. So let's use our definition again. So what do we have up top? We have a function of x plus delta x. So in our function, where the x goes, we write, so we have 2 times x plus delta x plus 4. I'm going to use square brackets now. Minus what? Minus f of x, which will be what? 2x plus 4. And what do we divide by? Let me extend that. We divide by delta x. Can we simplify this? We can. How do we simplify it? Okay, we can multiply this out. So what is it?
2x plus 2 delta x plus 4 minus 2x minus 4.
Everybody following? We happy? Divided by delta x. Can we simplify? Which ones? 2x minus 2x. 4 minus 4. Delta x and delta x. So what are we left with? We have the limit as delta x goes to 0 of 2, which is 2. 2, 2. Now, notice in this case, right, my answer does not depend on x. So we'll come back. Now, let's say I'm going to, instead of a number, I'm going to put m and c. So they could be any number. Yeah, I can do that. And let's put that in our equation here. So what will go here? I have a function of x plus delta x. My function is mx plus c. So in the x, I put x plus delta x multiplied by m. So here is m. And then I add c. There's c. And here, I do the same. Right? mx plus c. So now I have, if I multiply this bracket, I have mx plus m delta x plus c minus mx minus c. And when we simplify, what do we get? The mx minus mx goes away. The c minus c goes away. And the delta x cancels the delta x. So then I'm left with m. And the limit as delta x goes to 0 of m is just m. So we have just shown that the instantaneous rate of change, the derivative of a straight line, is indeed the same value everywhere as the slope of the line. Right? This is always true. For any numbers you take, you can pick any number m, any number c, positive, negative, real, irrational, fraction, whatever, this will always be true. And we can do this now, with let's try it with a different function now. I think we'll do one more example. So far we did a straight line and we kind of knew what to expect. With a straight line, we said, well, it seems pretty clear the slope will be everywhere the same. The tangent line, by the way, what does this mean about the tangent line? If I have the graph is like this, what is the tangent line at this point? If I have my function, this is f of x, this is my function, yeah, it's a straight line. I choose a point on the line, and I ask, what is the tangent of this to this point. What? Yeah. So in the case of a straight line, the derivative, the